Another video, another example. Let's go ahead and jump right into it. Here's our function 1 plus the square root of x, y equals 1, and x equals 4. We're going to be rotating out starting around the x-axis. Let's get a visual reference of really what this looks like. This is the square root function, square root of x, and we're going to shift it up 1. That means that I'm going to have a curve that looks kind of like this. I'm going out to x equals 4. It's going to go about there. So now I'm going out to x equals 4, and I'm bounded also by the equation y equals 1. So now we have this blue shaded area here in the middle. But just for some other reference, we need to see how high we're going here. We're going to be using that later as well. So this is y equals 1. This is at x equals 4, down here is 0, and this goes up to 3. Because if I were to plug in 4, 1 plus square root of 4 is 3. So that's what we're going to be starting with. Let's go ahead and go through our protocol, the questions we need to be asking ourselves. Does this shaded region, is it connected to my axis of rotation? Well, I'm rotating around the x-axis to start, and clearly I'm not connected here. I have some empty space in between. So I need to figure out what's going on with that empty space and how to set it up appropriately. If I have empty space in between, that means I'm going to have two radii that I need to calculate. I need a big R squared and a little r squared. I have the constant pi here. Since I'm rotating vertically, that means I'm traveling horizontally. So this is going to be dx, which means my limits of integration are also in terms of x. So I'm going from 0 to 4. So I just need to define my big radius and my little radius. Well, my big radius is from that curve all the way down to the bottom, and that would just simply be that whatever that curve is minus 0, which would be 1 plus square root x. The little radius is going to be here on the inside. Well, that's a boundary that's parallel to the axis of rotation, so it's just 1. It's 1 all the way across. It's going to make a cylinder. So little r equals 1, big R equals 1 plus square root of x. So my actual integral then is going to be pi times the integral from 0 to 4 of 1 plus square root x, quantity squared, minus 1 squared, dx. And there we go. That's part A. Let's keep moving. Same idea. Same function. Let's make this a little bit smaller so we can see it a little bit better. There we go. So we still have horizontal line, vertical line. We have the horizontal line y equals 2 as well. Or y equals 1, pardon me. And we have this curve that kind of looks like this. And then a vertical line coming down to 4. So let's go ahead and fill in our pieces. We know this goes down to 4. This is across to 3. This is at 1. 0 on the x-axis. And the y-axis as well. So again, we're finding this blue region. We need to figure out how are we going to rotate around this piece here, which is the line y equals 3. Well, immediately I notice again that I'm not attached. I have some empty orange coloring here. That is empty space that I got to cut away. So I know that I'm going to have pi times my big R squared minus my little r squared. That big radius is going to be from that axis of rotation all the way down to y equals 1, which in this case is 2. The little radius is this inside piece in the orange. And that's from 3, the line 3, y equals 3, down to the curve 1 plus square root x. If I were to simplify this, I would get 2 minus square root x. So that means my little r is 2 minus square root x. My big R is 2. And my limits are from 0 to 4. So let's go ahead and set that up again. That means I have pi times the integral from 0 to 4 of 2 squared minus, and then the quantity 2 minus the square root of x squared dx. How do I know I'm in dx? Because I'm still traveling in the x direction. I have horizontal axis of rotation, so I'm traveling horizontally. Okay, very similar here, but now our horizontal line is going to be a little bit higher that we rotate around. So let's start out with our x-axis, our y-axis. We have the line y equals 1. I'm going to color in these boundaries in gray. See how that works. There we go. So we can draw these in, differentiate the axes a little bit better. Then we have this curve. Let's make it a little bit smaller so we have some space up there for the line y equals 5. We got this vertical line at 4. Okay, so just to clarify here, this is 4, this is 0, this is 1, this goes up to 3, and then our axis of rotation is all the way up to 5. So we're going to be rotating around that line y equals 5. So we still have this blue shaded region that we started with, but now our rotation is going to leave a lot of empty space. Look at all this empty space here. So if we're trying to calculate that empty space, again we need to follow the pattern where we have big R squared minus little r squared. How do I know that I have boundaries in terms of x and functions in terms of x and dx? Because I have a horizontal axis of rotation, so it means I'm going to have vertical disks and travel in the x direction. I'm traveling from left to right here. So I start out at x equals 0 and I go up to x equals 4. I need to define what big R and little r come out to be. We have big R goes from the outer edge of the boundary here all the way to the axis of rotation, which is 5 minus 1, or just 4. Little r is on the inside edge to the axis of rotation. So it's going to be 5 minus, and then that function, 1 plus square root x. If I were to simplify that, it'd be 4 minus square root of x. So those are my two radius expressions that we need. Let's go ahead and fill out what the actual volume would be. The actual volume would be pi times the integral from 0 to 4 of 4 squared, that's my big R, minus the little r squared, which is 4 minus the square root of x, quantity squared, dx. Part D, now we're going to switch it up, start rotating the opposite direction. We're going to set it up with similar lines. So we still have that line y equals 1. We also have the curve here. We are still going out to the line x equals 4. And we still kind of touch here at 3, 0, and this is 1, and this goes out to 4. We still have this shaded region. Blue is the color of choice that we've been using for these. But now we need to go through our protocol as we rotate around the y-axis here. We need to ask ourselves, are we attached to our axis of rotation? The answer is no. We got this orange empty space in here. So when I try to find my big radius and little radius, let's go ahead and jump right into that. My big radius is going to be from the axis of rotation to the outer edge of the boundary. That's 4. My little radius is going to be this distance on the inside. It's the axis of rotation, which is 0, out to this curve. Now this curve is in terms of x, but if we're integrating in the opposite direction, we need to make it in terms of y. So it's going to be y minus 1 equals square root of x. Therefore, x equals y minus 1 quantity squared. So that's what this curve would be in terms of y. Now that's also the measurement for this radius on the inside, that little r. So that's going to be y minus 1 quantity squared. Then the volume is going to be, of course, pi times big R squared minus little r squared, which is 4 squared minus the quantity y minus 1 squared. This is in dy. We're traveling in the direction of y. And notice I'm only going from 1 to 3 here. I don't really care what happens down there. So that would be our answer for that one. Let's check out E. E is similar, but now we're going to spin in the kind of the other side of it. So let's set ourselves out with an x and y axis here. We'll go ahead and use gray for our curve. We have that line y equals 1 and x equals 4. And x equals 4 is actually the axis that we're going to be rotating around now. We're rotating around this line here. We still have this shaded region. So if I'm rotating around that line, it helps to realize that these values on the y-axis were 1 and 3. And that we're also attached. So I'm just looking at the pattern of the volume equal pi times big R squared from y equals a to y equals b. And we're doing dy because we're moving in the opposite direction, perpendicular. We're going vertically as we travel. So to figure out this horizontal radius, this big R, I need to figure out how far is it from this edge to the axis of rotation. Well, if we start with the bigger number, which is, in this case, 4, subtract the littler number, which is that function that we translated into y. If you think back to here, it's going to be y minus 1 quantity squared. So we don't really care about the little r, but we do care about this big R, which is 4 minus y minus 1 quantity squared. So our volume is then going to be the constant pi times the integral from, not 0, pardon me, from 1 to 3 of big R squared, which is 4 minus, then we got y minus 1 quantity squared, all of that squared, dy. One more and we are done. Now we're going to rotate around the line y equals 6. So let's start with an x and y axis. And we have our curve. We're going to do this in a gray shade here. I'm putting in my boundaries just like we had before. Those things haven't changed. But now we have a new axis of rotation that's a little bit further out. It's more about out here. And I know that because it says I'm rotating around the line x equals 6. That's that line there. We still have the same kind of boundaries where this goes from 1 up to 3. And I'm still doing this same blue shaded region. But now the difference is that we have a lot of orange space here in the middle. A lot of empty space where it's not connected. That tells me that my volume is going to fit the template big R squared minus little r squared. It's going to be a washer method. These are still in terms of y because I'm traveling in the y direction. So I'll have dy and my functions need to be in terms of y too. So let's start with the big radius. The big radius goes from this outer edge all the way to the axis of rotation. That means that I start with a bigger number, which is 6, and subtract the smaller number, which is that y function. And earlier we saw that that was y minus 1 quantity squared. So then the little r is going to be this inside radius from that closest boundary to the axis of rotation. And that actually remains constant because those two lines are parallel there. So that little r is just 6 minus 4, which is just 2.